Hello and welcome to the Daily Space for Tuesday, May 29th, 2018. I am your host, Dr. Pamela Gay, and as always, I'm here to bring you a fast-paced roundup of all that is new in astronomy and space science. So for today's top story, we bring you a story of Haze. Now, if any of you out there are following Planet Doctor on Twitter, you know that Haze is a thing that forms. Thank you so much, Satan, for the chair. If any of you follow Planet Doctor out there on Twitter, you know that Haze is one of those things that likes to build up around outer worlds. In recent research by her team and others, it has been found that we can now predict what kind of haze will build up around planets at different temperatures and with different compositions. In their research, they both ran theoretical models and they also used laboratory science to simulate how it is that particles form on, in this case, a plain old quartz crystal, when subjected to various temperatures and also to differences in metallicity. In this particular plot, the number you see across the top that is 100 times, 1,000 times, 10,000 times, that number is how much more metal rich each of these different samples are than our own solar nebula would have been. So you take the sun's composition, take the amount of metals that it has. This is everything more complicated than helium in astronomy speak. Take all of the materials that are more complex than helium and multiply their abundance by 100, 1,000, 10,000, and look to see what builds up in each of these different temperature regimes. Now, what they find is at particularly low temperatures. Here we're looking at things around 300 Kelvin. At these temperatures, we're getting larger particles. It seems the actual measurements, they look larger, but on average, the range of particle sizes actually isn't too different between the 10,000 and the 100,000. But basically, as temperature increases, the particle production decreases. This means that warm worlds are going to have less hazy atmospheres. Cold worlds, like Titan, which we see here in the background, are going to have more particles. It also means that the more metallicity, the more heavy atoms that are available to form particles, the bigger the particles are going to be within limits. There isn't a huge difference between the 1,000 and 10,000 times, so there seems to be an upper limit on just how big these particles are going to get. Oh, I'm being told my volume is low again. I'm fighting a bad cable. 1 second and I'll try resetting this. Okay, hopefully this is a little bit better. Sorry about that, everyone. Okay, I'm glad to know that helped. So if you want to find out more about this kind of research, follow Planet Doctor on Twitter and take a look at all of the papers that include Sarah Horst as one of the authors. I will say I picked this paper before I realized she was one of the authors, and then I had this moment of, oh, I know this person. So looking a little bit further afield, we have news from black hole research. In the past many years, astronomers using a variety of different telescopes to observe supermassive black holes in the centers of galaxies have been able to see about 24 events that we believe are related to the supermassive black holes feeding on a star that is in the process of falling into the black hole. Now, black holes don't actively reach out and yank stars out of their orbits, but Through a variety of different completely natural processes, periodically stars get sent, well, on a self-destruction path inwards towards the center of a galaxy. And when this happens, the supermassive black hole is there to happily feed upon the star. Now, in this artist's rendition, we see how a tidally disrupted star, a star that is literally torn apart by the difference in gravitational pull on the side that's closest to the galaxy and the side that is furthest from the galaxy, how it can get shredded and form a disk as it slowly spirals piecemeal into the system. Now, with the observations that we currently have of these 24 events, scientists have been struggling to make sense of the fact that in some of these observations, we see the light from this destructive event is dominated by X-ray light. In other events, we see that it's dominated by optical or ultraviolet light. In trying to make sense of all of these different results, a group of theorists working in a multi-international study that included the Niels Bohr Institute in Germany, Stanford, and Santa Cruz universities in California, they looked to build a unified model for what is the radiation, what is the spectrum of colors of light given off as the star is destroyed by the supermassive black hole. What they found was if you have a systematic way of destroying a black hole, destroying a star, so all stars are destroyed essentially the exact same way, but then you view this destroyed star from a variety of different viewing angles. What you're able to see as you observe the star being destroyed varies with, well, essentially where you're standing. From some angles, we see some colors of light blocked out by the intervening gas and dust of the galaxy. From other directions, we see straight down the throat of the accretion disk, and we're able to see different colors of radiation. So by building this systematic model in their software and then varying the viewing angle, we have finally figured out a unified model for how it is a star dies in a black hole. Now, this isn't the first time that we've realized that it takes varying your viewing angle in your model to get different objects to all behave the same way. For many years, in fact many decades, astronomers thought that Seyfert Type 1 and Seyfert Type 2 active galaxies were different kinds of things. In one case, you had narrow emission lines. In other case, we saw broad spectral lines. What was eventually figured out was it was just a matter of viewing angle, and these different kinds of spectral lines arose from different parts of the accretion disk surrounding an actively feeding black hole. So basically, it turns out these monsters in the centers of galaxies wear capes, and we can't always see all the colors of light behind the cape, but when we look straight down the mouth, that's when we get to see essentially all of the light. Now, in other, well, galactic news, there was a really short 3-page paper that presented these images taken from a variety of different public surveys. So this is where astronomers go out, and as a community, we dedicate the resources of given observational facilities to just look through the sky and take image after image over time. In these different survey images, it turned out that in an overlapping corner, they were able to see in all these different ways what turns out to be a background quasar that is getting lensed into 4 different images. And this particular object doesn't appear in the ultraviolet, which tells us it's at fairly high redshift. And it turns out sometimes all you need to do to discover these remarkable kinds of objects is write software to look through the surveys and look for specific kinds of things as a function of color and as a function of shape. Now, this is starting to open the door to entirely new areas of science that can be done. with machine learning that's being facilitated through the new Google public release of deep learning algorithms. In the near and perhaps now future, or I guess perhaps in the near future and the now in the present, astronomers are able to start looking through all of this publicly available data, one algorithm at a time, and turn up a treasure trove of objects that in the past could only be found by having individuals scan through the data image by image, which was time-consuming and expensive. While it's time-consuming on the short term to write this software, once it's written, we can turn it loose on all the new data that's coming out. So stay tuned for things we thought were rare showing up in the hundreds and hopefully thousands as more and more data is released. Now, in one final story, in this case a tale of planetary formation, astronomers looking out at a star called HD 163296 were able to image using the ALMA radio telescope, so the Atacama Large Millimeter Array, which is a series of radio telescopes actually. They were able to image a disk forming around this star, and in looking at it, they saw that it didn't fit the elliptical shape that it was expected to be. By studying this across a variety of different wavelengths that corresponded to corresponded to gas moving at a variety of different velocities, they were able to tease out, well, a kink in the data. In this case, an actual kink in the gas going around this star. The kink, they believe, is actually caused by what they have marked here in teal, a planet that is about 2 Jupiter masses orbiting around this young star. This is one of the first cases of being able to find exactly where a forming planet is in one of these protoplanetary disks. We've previously been able to identify them only after they had formed, or after the protoplanetary disk had formed into something more substantial. Here we are able to see a deviation in the velocity stream, in the way the gas is moving, that says, here be a planet. This is one of the earliest detections in terms of age of a solar system we have so far of planets forming in a young solar system. So yes, this kink is essentially tidal shear working on the orbit. So that's it for today's news. It was a slow news day due to the holiday weekend here in the United States. I suspect we'll be playing a bit of catch-up tomorrow. But for now, thanks for watching. This has been The Daily Space, a production of CosmoQuest. We are part of the Astronomical Society of the Pacific, a 501c3 that is dedicated to putting science in your brain. So if you like the show, give us a follow. Follows are free and it will alert you every time we have a new production going online. If you want to sustain our efforts, every subscription and every bit really helps. Now I'm going to go ahead and take your questions. So if you can @ me, it will really help me find your questions in the chat stream. So thank you all for coming today. I'm scrolling to see what I can find. Thank you so much, Peter, for your compliment. I really appreciate that. So I'm being asked for my thoughts on China opening their space station to the globe. I think that China is having this moment of realizing it's in a position to become a global leader through kindness. For a lot of decades, China faced a lot of shunning from different nations, including the United States, because, well, there were issues with trademark infringement, there were issues with military, we were concerned about war. There were civil rights issues. There continue to be civil rights issues. But In the days of Tiananmen Square, we had strict restrictions on our ability to work and share programs with China. This continues in a large part with the United States, where we have what are called ITAR restrictions on a great deal of technology. For a while, and I don't know if this is still true, it was actually illegal to take an Xbox to China because the technology in the Xbox was considered too advanced to potentially let into the hands of the enemy. Now, at the same time, for reasons that are beyond my political understanding, we continued to reach out and form new alliances with the Soviet Union and later the nation of Russia. These were space alliances, including the construction of the International Space Station. Now, during the construction of the International Space Station and continuing on to today, rules in the United States forbid sharing of this platform with China. So today, the Chinese have no choice but to go it alone in exploring our solar system and beyond. We have worked on a variety of different planetary satellites with them, but manned space, it's sadly us or them when it comes to the United States and China. Now, today we see that the United States political system is a bit different from it's been in the past, and I'm not going to expand upon that. And in this new political climate, China is working hard to show itself as a potential new leader. It's moving forward with global initiatives to change its production of greenhouse gases. It's looking to form new alliances and new trade unions. And now we see it also saying, hey, we're here to launch your vehicles, and we're here to, invite you onto our space station. For nations that are in the same boat as China and aren't allowed onto the International Space Station due to various governmental restrictions on the part of the United States, this finally starts to open space for other nations that just literally needed a foot up. So it's going to become a new space race, a new era, and for those who haven't been paying close attention, China's catching up. And Russia is no longer who we're going to be competing with. So in the past, we've seen competition has been good for causing and triggering advancement. I don't know quite what it's going to do today, but it is a new space future. Now, what other questions do you have out there? I'm looking to see. Okay, so Henny's Warverb is asking, since the Milky Way eats a lot of other galaxies and globular clusters, doesn't that mean there should be multiple supermassive black holes in the galaxy? This is one of those things that is often hard to sort out. We get regular press releases saying that Milky Way found to be cannibalizing another dwarf spheroidal galaxy. Milky Way found to be cannibalizing a dwarf irregular galaxy. A lot of these galaxies that we're in the process of eating and shredding into tidal streams in the process don't actually have black holes in their cores. Similarly, globular clusters appear to perhaps have intermediate mass black holes in some cases, but again, they don't have supermassive black holes. Now, we don't generally eat globular clusters, they just end up in orbit in the outer sphere around our galaxy. The dwarfs that we eat, they contribute their stars to our sphere and help puff up the disk of the Milky Way. But in none of these cases do we have the massive kinds of mergers that trigger black hole collisions. Now, there are galaxies that we see out there that have two similarly massed two similarly massed galaxies in the process of merging. In these systems, we do see the two supermassive black holes. And what we don't understand is what is the frequency at which these black holes get flung out during the merger process? What is the frequency at which they merge during the merger process? These are still things we're trying to understand. Now, we do believe that galaxies like our Milky Way were created through the slow merger of small galaxy after small galaxy after small galaxy. In this bottom-up approach to constructing a galaxy. Exactly how it is that we get the supermassive holes that we get, we're still working to figure this out. What we do know is the mass and the velocities of stars in the spheroids of galaxies is directly proportional to the size of the supermassive black hole. Where we see galaxies that don't have this bulge, this spheroid of stars in the center of a disk, we're not finding supermassive black holes. In massive ellipticals that are basically nothing but a sphere of stars, here we're seeing the most massive supermassive black holes. So we're starting to see the observational trends, but the details, we're still working those out. So I'm going to look and see what other questions have flown by. So Larry is asking, what are the little pea green galaxies? These are actually something that were initially discovered in the Galaxy Zoo project that I was part of many years ago. The little green peas, these are strange little elliptical galaxies that are still undergoing star formation. It turns out there is this set of galaxies that exist in the valley between the red galaxies and the blue galaxies, and these are our green peas. We're still working to figure out a full formation scenario for them, but science is a learning process. So Hanny is asking, why aren't all galaxies elliptical? This appears to be a question of angular momentum. If you get two systems coming in and colliding in the same plane, this process of conserving their angular momentum is able to build up a spiral structure. Now, we've found by observing galaxies across many different distance scales in the universe that where you have a pair of galaxies that probably formed out of the same rotating supermassive gas and dust, these co-forming galaxies will actually share rotational direction. It's possible that just as we end up with solar systems where all of the planets appear to be rotating in basically the same direction, we can also end up with small groups of small galaxies forming together in the same plane and then merging over time to form the bigger and bigger galaxies that we see today. Exactly whether this is true or not, this is going to be a question for the James Webb Space Telescope when it finally launches. It will have the capacity to look back to the early days of our universe and actually show us how all of these things really happened. I hope you're right, Paranor, that it's James Webb 2020, but yeah, we're not entirely sure. So I see Blebs 123 and Jay asking, how does one go about aligning a telescope for astrophotography when close to the equator? This is a hateful process. I don't know any other way to put it. The best you can do is line it up with a level, a compass, and a lot of corrections. GPS is really your friend in this case. And then you have to do a model of the sky. You jump from star to star and build up your pointing model by seeing how much you're off as you jump between stars. This pointing model will help you to figure out just how far out of alignment you may be and will help you develop a set of corrections. Ideally, you don't want to have to go through this process, but it's actually a good thing to have to do because it turns out that pointing alignments aren't just due to having the north pole of your telescope out of alignment. They can also arise because, well, your telescope may not be in the exact same balance as it slews to different parts of the sky. And this kind of a pointing model will help you correct for the fact that maybe when you're pointed off to the right, it slags a little bit down more than it does when you're pointed to the exact same altitude when you're pointed off to the left. So yeah, as you figure these different things out with your pointing model, it will help improve all of the astronomy you do. So good luck. And I wish you well. Developing pointing models is always a bit of a challenge. So what other questions do we have out there? I'm scrolling backwards to look and see if there's anything that I've missed. So I see that Friendring H asked early on, do we know what kind of objects provided mass to lens the quasar? Let me go ahead and pull that image back up. So in general, lenses are produced by a large mass galaxy intervening between us and the distant quasar. It's the mass from this large galaxy that's able to do the lensing that we end up seeing. With this kind of an image, I really can't think of anything else that could have produced the lensing, but unfortunately we don't really have the kind of spectral resolution on this that is necessary to really tease apart this system yet. This system was spotted in the Gaia data, and hopefully we'll get better results as we peer at this, perhaps a little bit more systematically and purposefully. Let's see, are there any other questions out there? So Hannes Vorwerp is asking, what is the biggest telescope you've used? So there's two different ways to use the word used. One is sitting at the control panel and slewing the telescope around with my own typed in entries at the control panel, and the other is submitting data for either a telescope observer. There's actually people that are assigned to operate the telescopes for you in a lot of different places, or submitting data to be used in a queue-based system where software figures out when and under what circumstances different objects will be observed. In terms of using a queue-based system, the biggest telescope I've ever used is the Hobby Eberly telescope, which is just over 9 meters out at McDonald Observatory. The largest telescope I've personally operated is the 107-inch telescope at McDonald Observatory, although I have been present and got to poke buttons, but I wasn't the one making the decisions at the 6-meter telescope in the Caucasus Mountains. I was there when it was the USSR. It's now part of Russia. I've used a bunch of telescopes, but those are really the biggest. Turns out the kind of science I like to do really wants a large field telescope, so I've gotten to use some pretty cool ones that are more in the 1 meter scale scattered around the planet. I haven't used the VLA. I've used survey data from the VLA. But I have to actually close this out. We are running out of time for today's Daily Space. Once again, my name is Dr. Pamela Gay, and this production is brought to you by CosmoQuest. Go to cosmoquest.org to find out how you can help NASA scientists explore our universe. We have scientists actively in need of more data on Mars and Mercury. So if you feel like helping us out, please go help us find all of the craters and other driving hazards and scientifically interesting features on these two worlds that begin with the letter M. CosmoQuest is brought to you by the Astronomical Society of the Pacific and a variety of partners all around the world. Later on this channel, you may see Matt Richardson, who is part of the Planetary Science Institute, Annie Wilson, who comes to us from Youngstown State University, and all of our other partners from all of the other institutions that make CosmoQuest possible. If you like what you see, again, please give us a follow. Follows are free and will alert you to all the shows that we have coming up. Our next show is going to be tonight at 9 p.m. Eastern, which is 6 p.m. in the Pacific and 11 a.m. tomorrow if you're in Sydney, Australia. I am going to be online doing a data visualization of a massive hot Jupiter going around a hot star, and over time I'm going to work towards, shredding this planet in my visualization. So tune in tonight, 9 p.m. Eastern, 6 p.m. Pacific, 11 a.m. tomorrow in Sydney, Australia, and catch some new science. Tomorrow I will be returning with the Daily Space, same time, same channel, and I will be followed up by Matt Richardson bringing you his Astro Office Hours. So thank you all for coming, and wherever you are in the world, have a fabulous morning, evening, or afternoon. And don't forget, look up. Bye-bye.